Okay, so the next law that we are going to discuss is about Gay-Lussac's law. So, Gay-Lussac's law was postulated by Joseph Louis Gay-Lussac. Right? So he was a scientist who investigated about pressure and temperature of a confined gas. Now, this one, it's not so easy to rationalize, but think about a pot that you are cooking, right? And inside that pot, there is water there and also trapped air. And obviously you are heating it up, right? So, what happens to the cover of that pot, right? Yes, so when the water inside boils, you can actually observe the cover going up and down because it's being pushed by the pressure inside, right? So from the perspective of the particles inside, when you heat things inside the gas inside the pot, the particles move faster, right? And so when they move faster, they hit on the walls of the pot, including the cover, faster. And so they create a greater pressure, right? And in the cooking pot, that pressure is released whenever the cover elevates. So when the cover actually temporarily raises up the pressure inside is released and equilibrium is achieved again. However, what if you fix the cover of that pot such that it doesn't move an inch? It will not give an opening for the pressure inside to be released. So what would happen? So just by logically thinking about it, doing a thought experiment, you would probably say that, when we heat up the contents inside, especially if it's a gas, obviously in my example, you have water inside, but you get the point, right? So if you have a gas inside, you heat the gas inside, the pressure inside will actually build up, right? Just like in the pot. And in fact, the only reason that the pressure there does not build up is because the pressure is released every now and then when the cover slightly gives a space onto which the pressure is released, right? But if you fix the cover such that it doesn't move an inch, doesn't move even a millimeter, then the pressure inside will keep on building up, right? Therefore, by logic, if you decrease the temperature rather, the pressure inside that pot will also drop. And therefore, we have this basic relationship, and therefore we can say that the temperature is directly proportional to the pressure. You increase the pressure, you increase the temperature, the pressure increases. You decrease the temperature, the pressure decreases. Now, since they are directly proportional, when this becomes bigger, that becomes bigger. So therefore, if I divide the two, so pressure divided by the temperature, that should give me a fixed number. So let me give you an example. If this is 10 and this is 5, 10 divided by 5 is 2, right? If this increases, the 5 becomes 20, right? The 5 becomes 20. This would also become 10. So now 20 divided by 10 is still 2. So that gives you a constant. And if that gives you a constant, then I can evaluate the pressure of a gas at a certain state and its temperature, and I can equate it to a second state of that gas. Say, for example, if we change the pressure, and I can see that both can be equated because, P1 divided by T1 is equal to that constant, and P2 divided by T2 is also equal to that constant. So if these two are equal to the same number, so we can equate them. Okay? So that is Gay-Lussac's law. Now, using that equation, we can now solve for certain um, word problems. Like, for example, what if the pressure is, say, 760 torr, and then the pressure 1, right? And then temperature 1 is, say, 800 Kelvin. And then let's say you change the temperature such that the temperature now becomes 200 Kelvin. Now the question is, what will be the pressure? Or maybe let's change it a bit. Maybe let's change the pressure. Maybe from 760 torr, we make the pressure 1520 torr of pressure. And then the question is then, how much is your temperature 2? So again, you just simply use this formula and say, hey, I'm looking for T2. So manipulating this formula, I would get, well, T2 will just simply be equal to P2 divided by P1 times T1. And then now I just need to substitute. So P2 is 1520 torr divided by my P1, which is 760 torr, and then I multiply that with my first temperature, which is 800 Kelvin. And then again, notice what is happening here. The torr is cancelled out with the torr at the bottom, right? And in fact, this is just twice of that, right? So this whole thing, when you divide, that becomes 2. So 2 times that would be 1600 Kelvin, right? So now you got the answer. But again, more than the calculation, just like before, you should be able to have this conceptual understanding of, well, yes, the pressure increased by twice as much. Therefore, there's no other way. If the pressure and temperature are directly proportional, then my temperature should also increase 2 times, right? So you see, even without my calculation here, just by logic alone, you would say if that becomes this times 2, then this should be multiplied by 2 and become 1600 Kelvin. But again, a precaution, word of caution: you cannot solve Gay-Lussac's law when you use degree Fahrenheit or degree Celsius. So you have to convert them to Kelvin first. Now, as an application, there are cooking pots in which the cover is actually fixed such that the pressure inside is not released, and that's what we call a pressure cooker. So if you are going to cook a certain meat, for example, meat coming from, at a 4-year-old, or I don't know, a 10-year-old carabao, which is pretty old, so the meat, the protein that you get from that is pretty tough. So if you cook it with ordinary pot, it would probably take you 10, 12 heatings and reheatings just for the protein to tenderize. But if you put it in the pressure cooker, close that lid, heat it up, Gay-Lussac's law works like magic. When you increase the temperature of the inside, the pressure inside also builds up, and that pressure actually would tenderize the meat in no time. So what takes you 10 to 12 hours in cooking, you can achieve that in maybe 3/4 of an hour or an hour to the max. So that's how Gay-Lussac's law. Obviously, in my example, you have water inside, you have the meat that's being cooked. But obviously, for a pure gas, the same concept still applies. Okay?